want to remind you that task number 3 is due tomorrow in the evening. I'll make it such that everybody can look after their labs have passed. And then there's a task 4, which I think you can start to think about around tomorrow. And you'll have until Wednesday night next week to do that. Of course, we're 9 days away from the spring break. And also 9 days away from exam 2. No, you should be thrilled by the prospect of exam 2. It's a challenge, it's a good challenge. It will be. I have on my side, I have 2 things still to do. Or maybe 3. I need to upload some extra practice questions that will help you for the exam. I will post a practice exam also. And the final lecture notes for what we will go over before the spring break, and that will be the active science calendar. So we'll get there. Okay, we're looking at respiration, the mechanism of ATP synthesis, etc. That's called chemiosmosis. And we've seen there's a Scotsman, Peter Mitchell, and he proposed the mechanism of chemiosmosis. And it involves the generation of a proton gradient. Essentially, the energy taken from the gradual stepwise breakdown of organic molecules, such as glucose, fatty acids, and energy is temporarily stored in a proton gradient over the mitochondrial inner membrane. And then that proton gradient, that energy is harvested in order to drive the synthesis of ATP. So to understand that mechanism, we must understand how the proton gradient is formed and then how ATP is formed using that proton gradient. And we see that electron transport is the mechanism that drives proton gradient formation. Electron transport from reduced coenzymes such as NADH to oxygen. Now in that electron transport chain, there are macromolecular complexes. There are 4 of them, but we can say that they function in 3 stages. So stage 1 is complex 1 and complex 2. Complex 1 accepts electrons from NADH, complex 2 from FADH2. Both these complexes reduce a quinone, ubiquinone. Then there's complex 3. Complex 3 accepts electrons from ubiquinone and reduces cytochrome C. Cytochrome C sits in the intermembrane space outside of the matrix. Cytochrome C then reduces cytochrome C oxidase, which ultimately reduces oxygen to form water. The complexes 1, 3, and 4 force the cytochrome C oxidase, move protons across the membrane. And the question is, what could be the mechanism? One mechanism is what Mitchell called a redox loop mechanism. And it involves the idea that the quinone picks up protons on the matrix side and releases them on the transmembrane side, or the intermembrane space side. Let's say here we have a membrane. There's a complex in it, that's complex 3, which accepts the electrons from the quinone. The quinone was reduced on the matrix side, where it picked up the protons and the electrons from somewhere else. It gives its electrons to complex 3, it then releases the protons on the other side. That's called a redox loop. This is how complex 3 moves protons across the membrane. It's not really pumping this mechanism, but it's driven still by the difference in redox energy between oxidized and reduced phenol. Okay, so that electron, or those set of electrons, from complex 3 are then given to iron, which sits in heme, which sits in cytochrome C. So that iron 3 becomes reduced to iron 2. And those electrons are then given to complex 4, ultimately leading to the reduction of oxygen. And it seems that complex 4 functions really like a pump, meaning it has different conformations where it can bind protons and then change conformational shape and allow the protons to be released on the other side of the membrane. There's some similarity between this mechanism for complex 4 and the mechanism by which the sodium-potassium pump moves the sodium and potassium, because it's a conformational change in the protein. But here the energy comes from the electrons. So we call this a conformational pump idea. It's also thought that complex 1 functions by itself as a conformational pump. Between different textbooks and in the literature, there's some discussion about how many protons are pumped at each complex. I think the correct numbers are 3 or 4 for complex 1, 3 for complex 3, and 4 for complex 4. And that means 10 in total, approximately, let's say 10, for each NADH that is getting oxidized. The book gives sometimes slightly different numbers. I'm not really sure if they're right. Okay, but the key point is that mitochondrion pumps protons across the inner membrane. So can we see that? Yes, it can be observed. Here's the setup. Mitochondria can be isolated by centrifugation. You grind up cells, and by centrifugation you can isolate the intact mitochondria. You can provide the mitochondria with oxygen, and that oxygen is an electron acceptor. And then you can observe that there is a change in the proton concentration in the medium by having a pH meter here sticking in our tube. So this is a tube. The tube is closed at the top to allow the oxygen to stay in. And you can see a temporary change in the proton concentration in the medium, meaning protons have been moved out of the mitochondrial matrix. So the big question to you is, what else must have been present in this system here? Except for intact mitochondria, which are isolated, therefore removed from the cytosol, and oxygen, what else do we need to give in this system so that we can see this movement of protons? That's something to think about. And I'd like to think while I walk back and forth. There's not one right answer. Okay, so any idea? Any suggestions?
ADP.
ADP. I think is a great suggestion. Why did you say ADP?
Because then it's coupled to the electron transport.
Yeah. That is actually, I really like that answer. What else? Because I have more. Glucose. What would happen if we give glucose to mitochondria? Can the mitochondria break down or use glucose? I see a lot of no's. Why do you say no? Sorry to put you on the spot. Yes.
Okay. Because the glycolysis happens in the cytoplasm of the cell and not the mitochondria.
So yeah, the mitochondria are isolated, so the cytosol is gone. So we don't have the 10 enzymes of glycolysis here. What we need to give to this mitochondrion is some kind of a substrate. Anything that enters a Krebs cycle. And you can give it pyruvate, or acetate, or even citrate, or another intermediate of the Krebs cycle, which it needs in order to reduce NAD plus to NADH, which it can feed into the electron transport chain. So I want to come back to this idea of giving ADP. So let's say you are giving ADP. Would you think that we would see as quick a rise in the proton concentration on the outside?
No,
Because
that's a good question.
well, let's think about it this way. If we give ADP, then there is reason for the mitochondrion to, as a substrate for the mitochondrion to synthesize ATP, and as we'll see in a moment, that takes the proton gradient back. So actually, if you give ADP and PI, inorganic phosphate, together, then the mitochondrion will move protons across, but also back into the matrix. So you don't get that excess. So why this concentration here is going down is actually those protons might somehow leak back into the matrix. Maybe because there's a little bit of ADP somewhere here in the system, I don't know. So we need a substrate. This is the big answer here. So we need a substrate for the mitochondrion. If glucose won't work, acetate would work, pyruvate would work, citrate would probably work. An intermediate of the Krebs cycle in general would be good. Alrighty? If you would give ADP and PI in addition, actually you would get less of a rise in the proton concentration. Probably. Alright. So complex 3 functions as a proton mover and moves protons by means of what we call the Q cycle. It's a redox loop. Now, for the aficionados, 30 seconds, and you don't have to know for the exam, but it's still interesting and insightful. So what drives here the reduction of this complex and the oxidation of ubiquinone is the difference in redox energy or electronegativity between all these iron-containing groups in complex 3 and ubiquinone. Now, it turns out that there are different iron centers, cytochromes, in this here complex 3, and they have a different standard redox potential. And one pathway has a pretty big drop, and that electron goes on to cytochrome C. But there's another pathway here to cytochrome B, which goes with a small drop in energy content. And that means that the electron still has a lot of energy. So, ubiquinone is here oxidized. The 2 protons are removed from it and they're moved to the intermembrane space side. 1 electron goes in a deep hole, disappears. The other electron can be reused together with a ubiquinone that has been half oxidized. And that actually means that a 3rd proton can move across. So I don't think this diagram is correct. I think there's 3 protons that are moved net. Complex story. The oxidation of ubiquinone is a 2 electron oxidation step. 1 electron loses a lot of energy, the other doesn't. And actually the loss of the proton has already occurred. We can still reduce that same quinone with 1 of those electrons. And then we get a 3rd proton across. So, bottom line is, it's thought by me that this complex moves 3 protons per ubiquinone. And it's a complex pathway, it's all redox loops. Okay, enough about that. Complex 4 is also known as cytochrome C oxidase, and it functions as a pump. It must be a conformational pump. Here is the assay, the test. We can make vesicles that have cytochrome C in there. In some biochemistry labs, this is a first year, second year student experiment. You can obtain cytochrome C oxidase, put it in a vesicle, and if you give reduced cytochrome C, so that cytochrome C has to be reduced, then the cytochrome C donates electrons to this complex. Ultimately, this leads to the reduction of oxygen to water. That takes 4 cytochrome C electrons, so 4 reduced cytochrome C proteins have to come in. And when you do that, you can see a proton pumping. And that proton pumping can be seen by a change in the pH. So the pH actually lowers. Here we're measuring the pH change, not directly proton concentration. Of course, it's the same. So if we give oxygen to this system here, and we have given reduced cytochrome C, we can see a pH change. So this is evidence that this here functions as an electron-driven conformational pump. There's some leakiness in the system, so after a while the protons move back in. Now in this system there is also this valinomycin present. Valinomycin is present there in order to make the measurement possible. The question is why? And why is valinomycin added in this system? What you have to think about is that if protons move, then that means an electrochemical gradient is built up, and there are 2 components to that electrochemical gradient. And remember, it takes very few ions to get a significant potential. So why is valinomycin added? I'll go. Alright, I found the point. So why was valinomycin added? So remember what valinomycin does. What is valinomycin doing? Pathway for potassium, right? So there's a pathway for potassium to move over the membrane. So if we move protons by cytochrome C oxidase, we establish a membrane potential. A membrane potential establishes very quickly. So there's a significant membrane potential. At some point it's so steep you can't move protons against it anymore. Our measurement becomes very insensitive. But if we provide a pathway for potassium to leak out, potassium will leak out of the vesicle in order to, and in response to the membrane potential actually. So you dissipate the membrane potential, you take that away with valinomycin, if there's potassium in your buffer. Meaning that your electrochemical gradient will be mostly a proton gradient, and therefore measurable in this system. Now I'm thinking of an exam question. Had we done this experiment without valinomycin, could we measure an electrochemical gradient in this system? Yes, we could. We could have used TPP+. In that case, it would be unwise to add valinomycin, because then we can measure directly with TPP+, the steepness of the membrane potential. This one and this one are two questions to think about, to understand. You should be able to explain this to your girlfriend, boyfriend, son, daughter, mother, father, granddad, or in the absence of that, your dog or cat. Or any imaginary friend. Also. Alright. So, proton moving systems create a proton gradient. Good. How is that proton gradient used to synthesize ATP? Well, there's another complex, a fifth complex, that we call the ATP synthase, and it's very well studied, and it's called the F1-FO ATP synthase because in EM pictures, it appears as if there are two parts, one part in the membrane, and we think it's the channel part, and one part that sits on top on the matrix side of the inner membrane. And that is an enzyme that can utilize ATP, break it down, but it can also form ATP from ADP. So we call this enzyme the F1-FO enzyme, ATP synthase. And this is a model based on partial structures of the different parts of the enzyme that have been examined by electron microscopy and other parts by X-ray crystallography. So the idea is that ATP synthase should couple the backflow of protons to ATP synthesis, and it's doing that. And we know that it's doing that because we can take membranes. Unfortunately, this picture is not in the book. I like it. They can take mitochondrial inner membranes. They can be isolated by centrifugation. They can shape those membranes, and you get small vesicles like this, which are inside out, as we say it. So that means that now the matrix side of the membrane is exposed to our outer medium. So remember, in ATP synthase, the F1 part, that sphere, is in the matrix originally. This is a mitochondrial inner membrane, intact vesicle. But if we shake it enough, we get these inside-out vesicles. So the F1 part now sticks out. Now if we shake it really hard with ultrasound, actually the F1 part falls off, and you get separate F1 particles, and vesicles with these FO parts in there, which we can see in an EM. They look like these channels. Now, these channels actually are leaky to protons. They're channels for protons, that can be measured. And the F1 parts can degrade ATP, forming ADP and PI, or the other way around, depending on the conditions that we give. So this is an ATPase enzyme. If we put the two together, now we can have a system where if we have excess of ATP, it pumps protons in. If we have excess of protons in the vesicle, and if we have ADP in excess on the outside, then the protons move out and the ADP is combined with inorganic phosphate to form ATP. So in the combination, it works. Now, there are lots of, I don't want to go too much into detail of how this system works. The idea is that the FO part, the channel part, is linked to a system that makes for a rotation that generates or affects, if you want, the binding sites of ADP and inorganic phosphate on the F1 part. And what essentially happens is proton flow affects the conformation of critical subunits in the F1 part, which essentially bring ADP and PI so close together that by the rules of chemical equilibrium, there's no other choice for the two to combine and form ATP. So you generate a locally high concentration of the two, you get ATP formed, and then in the next stage this is released. And it's known that this involves the rotation of a part that's called the stalk that connects between the FO and F1 part. That's it. You can read more about that in the book. All right. I've also sometimes skipped parts about how the ion channels work for sodium and potassium in the nervous system, and how they are gated and how we get the refractory periods. You can read more about that in the book. I can't go over everything in class. Now a couple of notes. Now we've had the system. You know how it works. That electrochemical gradient across the mitochondrial inner membrane that we see here, that electrochemical gradient of course has two components. There's a pH change and there's a membrane potential. But in this system, it's mainly a membrane potential. The reason for that is that there are very few channels in this system that allow ions to leak. And therefore, the membrane potential builds up very quickly to the transport of very few protons. So why does it make sense to have not a big pH change? You have to remember that the mitochondrial is an outer membrane that has large pores, and the protons could just leak into the cytosol. We don't want a big acidification of the cytosol. So maybe there's a reason why there are not too many protons moving across. So that electrochemical gradient mainly is the membrane potential. Now, this membrane potential is of course positive out and negative in the matrix. It favors the export of ATP together with a simultaneous import of ADP. Because ATP is more negatively charged than ADP, and because of the membrane potential, in this carrier right here, because of the membrane potential, that more negatively charged ATP is pushed out of the matrix. The membrane potential is positive out, negative in. Okay? Alright, there are other carrier systems in the inner membrane that we also have to think about. Now let's look at the efficiency of this process of chemiosmosis. So, it's pretty well established that for each NADH that is oxidized, that 10 protons are moved. So I think it's 3 at complex 1, 3 at complex 3, and 4 at cytochrome C oxidase. So there are 10 NADH actually in total for each glucose, so that's 100 protons, 10 times 10. Then there are 2 FADH3 which are also used, and let's say that it's 6 or 7 protons. I'm saying 6 here, it could be 7. So if we add that up, 100 and 2 times 6 is 112. Hey, it could be 114, who cares? We have roughly 112 protons per glucose. Alright. How much energy is in there? Let's think about that. Now, if the electrochemical gradient, if that total proton mortar force is roughly 180 millivolts, which is close, then that means that we have for each proton roughly 3 standard packages of energy. Good on that? So if that's true, then we have 3 times 112, that's roughly 330, 340 packages of energy. If you can follow. And if you cannot follow, you should do it again at home. Watch the video. Now, how much does it really cost the cell to make ATP from ADP and PI? There's a standard Gibbs free energy of 7.3 kilocalories per mole, but because in the cell there's an ATP over ADP ratio that is between 100 and 1,000, a very good estimate is 11 to 12 kilocalories per mole, and that equates to 8 to 9 standard packages, with the standard package of energy being 1.4 kilocalories per mole. So if we do the math, we have 340 packages in the proton gradient, And if we need 11 to 12 per ATP, then you can make roughly 37 ATP by oxidative phosphorylation using the proton gradients in the mitochondrion. We got another 2 in the Krebs cycle, and we already got 2 in glycolysis. So according to this math, we might be getting something like 41 ATP per glucose, but we're getting less. You know, we're getting much less. So why do we get less? Okay, another way to say it, if we just think that if there's 180 millivolts membrane potential, then 3 protons should be enough to drive the formation of 1 ATP from ADP and DI. So there's 3 packages of energy in each proton. We need 9 packages. 3 times 3 is 9. 3 should be enough, but it's actually not. It seems like it's not. So why is that? What is going on? There are a couple of reasons, and 2 are on here. The first one is that the ATP synthase might actually need more than 3 protons, it just might need 4. But in addition, there are some channels in the mitochondria sometimes called leaf channels, and these have a name. They're called uncoupling proteins. What is their function? If we have channels in the membrane and we lose our potential energy there and we generate more heat, what is the function of that? Well, you actually want to stay warm, especially if you're a bear hibernating and it's pretty cold, you want to stay warm. Or if you're a baby and you have a small body, you need to keep yourself warm against the elements. So these channels, these uncoupling proteins, as they're called, are actually present in the mitochondria of mammals to different extents. But they're especially present in brown fat tissue, which is found in hibernators, and it's found in young mammals that need to stay warm. So just to generate